the last week of classes. We are done with our last unit there, the sequences and series. And I see several people have not taken the test from last week yet. So I got all the grades updated in Hack, and it brought a lot of grades down if you have zeros for this last test. So grades went. So need to get that turned in. Let's talk about next week. Next week is final exams. Woo, woo, woo. Oh, okay. Maybe not everyone gets excited about final exams. Your number one goal, of course, is to be exempt from final exams. But if you've already had too many absences, that's not going to happen. I will be sending out emails on this Friday with the official yes, you're exempt, no, you're not exempt statements there. So I will get a report with all the final attendance records for the semester and send it out. So let's see what happens. If you are exempt, that means you have no more than 4 absences and no more than 4 absences in advisory. You can have 4, just not more than 4. And that means you have no missing assignments. All the way, go into Buzz, go to that grade screen, go back and look, make sure there's nothing down there that's missing. And also means no fines or fees, which we don't have in this class. And the last thing is your grade must be 75%. So if you don't have more than 4 absences and you don't have any missing assignments, but your grade's a 72, get your grade up. Go back and look and see, what did I score poorly on? Oh, I need to redo that. Go redo it. Get your grade up to 75. Then you can be exempt because you can meet all those qualifications, right? But if you are not exempt, which, I see some people that could be exempt, but they've got missing assignments. So you really should go back and check on that. I see a couple of people have not been absent, but they are missing things and will end up taking the final because they're missing something. Some of it's just one assignment. A lot of people skipped 5.06 way back at the beginning of the semester, which was something you had to actually do on a Google Doc. And it's like, oh, it's not just a 5-question quiz. I'm not going to do it. Well, now it's going to bite you in the rear end because you're going to end up taking the final because you never turned that in. I see at least 3 people that could be exempt that don't have everything turned in, including all 3 of them have that 5.06. But anyway, moving on. If you do have to take the final, this is how the schedule works this time. Next week is finals week. We will meet as a class, 5th period, which I put this on the front page of Google Classroom, the final exam schedule. This class is scheduled at 9:15, a little later than usual. 9:15 on Tuesday, the very first day of finals. The very first day of finals. So you will come to class at 9:15 on Tuesday and take the final, unless you get up earlier and already have the final done by class time. Because the final will be available Tuesday morning, starting at midnight in the morning. So you have all from Tuesday morning, midnight, until 9:15 on Tuesday. This class meets at 9:15, and you'll take the final during class, unless you've already got it done. Regardless, it's due, all finals are due Thursday at 11 o'clock in the morning because we have to turn grades in on Thursday. So our class is scheduled Tuesday, so we should have the final done Tuesday. Come to class, 9:15. If you're exempt, I won't see you Tuesday. You run off and have a great summer. If you're exempt, you don't have to come. This week is an A-Day Friday, so we only have class today and Thursday. For those of you whose grade has dropped below 70% because you never took the test, last week was the test, and a lot of you people dropped because I see a lot of zeros and people didn't finish the test. Probably half the class. Half the class didn't finish it. Now, some of you did part 1 and didn't do part 2, but that's still, you haven't finished the test. So there's some people like that. All right, so where does that leave us now since the test was last week? I have an assignment for you this week, and it's kind of a fun project and can boost your grade because it's worth like 50 points. That's like half a test grade, which means if you don't do it, then it's 50 points negative. You 0 out of 50. That's going to hurt your grade even more. So let's do this project. Very simple, fun project this week. fun project. So let's take a look at what we have this week. I'll put it up on the screen. If you go to Google Classroom, if you go to Buzz, it doesn't help you that much this week because you need to be here to know what we're doing. Let's look at fifth hour. Go to the grade screen. Here's where you look to see, am I missing anything? Nope, that's submitted. That's submitted. There's check marks there, but there's no assignment there. That's just a folder. Nothing, no zeros, not missing anything. Great. All right, all we have left, other than the semester final down at the bottom, is the golden ratio assignment. It's a project. See right above, it's a project. So let's go look and see what that looks like. Back on the activity screen, we can close sequences and series. If you've done the test, you're done with that. There's the golden ratio project. We have the lesson and the assignment. Lesson. There's not much there because we're going to talk about this in class. I'm going to give you your assignment in class here. We're going to review this in class. We're going to talk about the Fibonacci sequence and the golden ratio. And by the way, which one of these rectangles looks right? Looks correct? Which is the right one? Turning in this, you just over here, you'll do this as a Google Doc. But I want to talk about this assignment this week. What in the world are we doing with this assignment? All right, let me put this up on the screen. There we go. Okay. Which rectangle looks like it's the correct way to draw a rectangle? You're like, well, that's I've never been asked that, Mr. Brock. That's kind of weird. Well, it turns out years and years of study, and people study everything, weird things, have determined that there's one shape of rectangle that people like better. It's more pleasing to the eye. It just looks correct. The other ones just look like, okay, that one's just, that's not a nice rectangle. Like, J is a really, really long rectangle. A is almost a square. Yeah, we have a lot of different rectangles. So I'm going to put a poll up here. So go down by the chat with that little triangle, square, circle emblem. And I've launched a poll. And I want you to vote on which one of these rectangles is the most pleasing to the eye. And of course, I have someone in this class who would vote for J, but if I just didn't show this and ask you to draw a rectangle, you never would have drawn J. You would never have drawn J. That'd be interesting. I should have people draw rectangles next year. I may redo this. I want to redo this next year just because I wonder if people are influenced by where it's shown there. So, all right, we got several votes. Nice. And one voted. And one voted it wants to vote. Most of our votes are right in the middle. D, F, and G is getting most of our votes there. We've got a few votes on the outside. C and D are almost identical, it looks like. But yeah, there's a vote for C. There's a couple of votes over on the right-hand side, H, I, and J. Got some votes kind of all over the place. Nobody said A or B. Nobody liked A or B. Most of our votes are right here. Well, let's talk about this because there's some interesting math that goes on with all of this here. I want to talk about a guy named Leonardo. He discovered this sequence of numbers that math calls the Fibonacci sequence. Now, Fibonacci was the name that he published this in the mathematical journals at the time because people would publish their math. And his name was actually Leonardo. He lived in Pisa. When he was a young boy, they were building the Tower of Pisa, which we now know as the Leaning Tower of Pisa. It just wasn't leaning when he was alive. But he lived 800 years ago, 1170 to 1240. So this is 800 years ago that this sequence was discovered. And his sequence starts out, you can see at the top of the screen there, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. It just keeps going from there. It's called the Fibonacci sequence. Now, when he came out with this sequence, he was ridiculed, and other mathematicians like, that's a bunch of garbage. What are you, a moron? That's just foolish. That sequence has no purpose. You don't know what you're talking about. So he published under the name of Fibonacci, which in Italy is like foolish, fool, a fool. So he used this fake name called Fibonacci, although his real name was Leonardo. But let's look at his sequence that he discovered. Like I say, he discovered it because it exists. He didn't create it. And we'll see why as we go through this. Here's how his sequence works. You start with a 1 and another 1, and then you add them together. And that gives you 2. So then you always take the last 2 numbers and add them together to get the next number. So 1 plus 2 is 3. So 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. And so on and so forth. 144 plus 233 equals 377. So the next number in our sequence would be 233 plus 377 would be 610. And it just goes on and on and on and on. 987 after that. This is known as the Fibonacci sequence, a very famous sequence in mathematics. If you go to college, some of those math classes dig into this even more. But I want to look at this as an illustration. See all these numbers back here. If we took and made boxes, squares, that had those dimensions, a 1 by 1, a 2 by 2, a 3 by 3, a 5 by 5, an 8 by 8, it would look something like this. We start with the 2 1 by 1s. Put them side by side. That makes a rectangle. Then we're going to put the 2 by 2, and that makes a new rectangle. And with the 3 by 3, that makes a different rectangle. Now you're going to put the 5 by 5. You'll see that rectangle there, the big rectangle. Then the 8 by 8 and the 13 by 13. And notice it's the same length as the boxes before it. You just keep adding as you go. And this keeps making different rectangles until finally you got this great big rectangle with other smaller squares inside of it that also make rectangles. So this great big rectangle actually has a very interesting property to it, that it is what we now refer to in math as the golden rectangle. Like the golden rectangle. Yes, the ratio of the length to the width, if we take how long this is and divide it by how tall it is, it gives us a certain ratio that is known as the golden ratio. Now, this rectangle right here, many, many mathematical studies have shown that this apparently is the most pleasing rectangle to look at. It's the rectangle we like the best. And it's kind of interesting. We can also take this Fibonacci sequence of squares that make these rectangles. And if we start with the little bitty ones where we started building this, the 1 by 1s, and we make a line that connects corner to corner, but do it like a circle. Just connect all the corners by circles diagonally through each box. I'll show you what that looks like. So we start with the small ones in the middle. Now go diagonally across that square. Go diagonally across that square. Go diagonally across that square. And this begins to spiral outward as you connect diagonally through each one of the squares formed by the Fibonacci sequence. And this has become known as the golden spiral. See, it spirals out, and it's a golden spiral, and it's very, I don't know if it's the most pleasing spiral, but this is all around us. This is found in our world. This is found in nature. This is found in the universe. This spiral exists in a lot of places. So that's why I said when I said that Fibonacci didn't create this sequence. He discovered this sequence because this exists. So looking at each one of these now, each one of these squares, we could take the area of a square, right? All this 1 by 1, 2 by 2s, 3 by 3s, 5 by 5s, 8 by 8s. We take the area of like the 5 by 5. We know it's 5 squares wide and 5 squares tall. So we know the area is 25. And then the 8 by 8, we know the area is 64. So if we look at the area of each of these, the 5 by 5, the 8 by 8, the 13 by 13, starting in the middle again, you have the area of 1, you have the area of 4 on the 2 by 2, area of 9, area of 25, and we can continue going 36, 64. But there's something interesting when you take this sequence and start comparing the areas. Take 89 and divide it into 144. It's 1.618. If you divide it the other way, it's 0.618. 1.618 and 0.618. And keep going. Take the 233 and divide by 144. 377 divided by 2. This is called the golden ratio. This is the ratio of the numbers compared to each other. And when we look at these rectangles, D is actually the golden ratio. That is actually the dimensions of the golden rectangle. And we had votes for D. We had a lot of votes right there in the middle of the screen. D and F had some of the most votes. And that is the golden rectangle. It's the most pleasing to the eye, they say. And you're like, okay, that's fine. These studies show that, but why does that really matter? Well, the Fibonacci sequence itself is found, like I said, this is found in nature. We look at trees. Let's look at a tree. The sneezewort trees is a great example of this. Not all trees follow this, but a lot of trees follow this. If you look at how many branches they have as you section it off going vertically, they start with one branch and then it has 2 branches when it breaks off there. Now it breaks again, has 3. Then it'll do a double break, have 5. Then it'll have 8 and have 13. And notice this, these are the numbers of the Fibonacci sequence. The 2, 3, 5, 8, 13. The next one will have 21 when it branches off again above that. And root systems follow this same thing. You can see it in the root systems of plants and trees. It's interesting how you find this in nature. You're like, okay, well that's kind of neat. Well, let's look at the Mona Lisa. Arguably one of the most famous paintings in the world, the Mona Lisa. When you take the golden spiral, the proportions of which she's painted fit a lot into that golden spiral. The size of her head fits the height of that golden spiral. One of those golden rectangles, if we took this green rectangle right here and moved it, shifted it over just a little bit, we'd find that her face and head right there fits perfectly inside that golden rectangle, the right ratio, the proportions that we find most pleasing. Maybe that's why this is one of the most famous paintings in the world, because people just like it and don't know why. It's math. That's why you like it. Going back thousands of years when they built this in Greece, go over to Greece and see the Pantheon. The proportions, the size, the ratio that they built the Pantheon, if you look at the width and the height, it matches that golden rectangle, that golden ratio that we like, the length to the height. It's like, wow, okay. Well, let's look at nature. When you take a nautilus shell and you cut it open, you start seeing that golden spiral forming inside the nautilus shell. We also see that golden spiral in butterfly wings. The human ear, the average human ear, now, of course, there's different shaped ears. Some people have ears that don't fit, but the average human ear perfectly fits the golden spiral. Here's the ones I really like here. Hurricanes. Look at the shape of a hurricane taken from space. Looks like a fancy shell, doesn't it? Yeah, that spiral does look like a fancy shell. Hurricanes, galaxies. Look, you impose that golden spiral on a galaxy or on one of those satellite images of a hurricane, and nature is perfectly mimicking what we learned from the Fibonacci sequence. Fibonacci discovered this. He found it in nature. It's happening all around us. There's something to the math of this sequence that just happens. It's really, really cool when you think about it. And here, let me get it down to something that even the most basics. Let's look at a strand of your DNA, human DNA. If we look at the height of a strand of DNA, it's 21 angstrom units wide. And let's follow one DNA strand. So it's at the bottom, it curls up, it curls back down. So that would be 1 unit, right? That would be one strand of DNA as it completes the circle. It's 34 angstrom units long. And look what happens when you divide the length by the width of a strand of DNA. 1.618. Pretty wild. It's all around. Math is just all around us, and it's consistent and it works. It's the math. So, with that, let's talk about your assignment for this week. You'll need a tape measure, a ruler. What you're going to do is on a Google Doc, you're going to submit 3 pictures of things you find. You can find them around your house. You can go out in the community and find things. You can find advertising that fits this. Advertisers know about the golden rectangle, golden ratio, what looks right to people, what appeals to people. But you're going to find 3 items, take pictures of them. Could be in nature, architecture, logos, art, wherever. And if you find golden rectangles, that's what you're submitting, but you need to give me the measurements. I need to be able to say this divided by this, that's about 1.6. It's not going to be exactly 1.618. It's going to be really close, though, about 1.6. If you get it close, that counts. And if you find golden spirals, there's nothing to measure. You don't have to measure golden spirals. So if you submit pictures of a golden spiral, you don't need to submit any measurements. Only the rectangles do you need to submit measurements. But let me show you something. When I was talking about how advertisers and companies understand this, they understand this. They know what's pleasing to the eye. So let's go to the basics of what appeals to people. Here's my debit card. Pull this out of my billfold. Let's measure this in millimeters so we can get as accurate as we can. 85. Okay, that is 85 millimeters. I'm going to pull up my calculator right here. My debit card is 85 millimeters wide. So how tall is it now? 53. It's right at 53. So let's divide by 53. And look, a credit card, a debit card is 1.603. Right at the golden ratio. Right at the golden ratio. So advertising, you can find logos. You can go look at logos of companies, and not all of them do this, but a lot of them will have that golden spiral or that golden rectangle comparing the height to the width. If you divide that, just like I divided this credit card, this debit card, you'll find it's about 1.6 because they know it's pleasing to the eye. They study this. They go get degrees on how to appeal to people and market products. And one thing is to make it pleasing to the eye, and this golden rectangle is used a lot in advertising, in logo design, in website design. So you just need to go find 3 pictures of something that fits that golden ratio, the rectangle or a golden spiral. It's interesting if you look at flowers follow the Fibonacci sequence. There'll be a lot of them that have 5 petals, 8 petals, 13 petals, 21 petals. The seeds sometimes inside flowers in the middle of them follow that golden spiral. It's nature and it's math and it's all around you. What's up, Jonathan?
What? How close do we have to be at 1.6? Like how many?
If it's 1.4, that's not a golden rectangle.
Okay.
So you got to judge it. It can be 1.67, and that's fine. 1.54, so not exactly, but you'll find it something really close. And I've had people that found stuff really fast with this. But yeah, just get something close to that 1.6. Because like I say, getting it exact, you got to be able to really measure precisely sometimes to get if you're going to try to get 1.618. But find something close to that because it's used all over. It's used all over the place. And again, it's in nature. You find a lot of things in nature that have that spiral or that golden Fibonacci sequence in there. So neat stuff. Easy points, 50 points, guys, just to submit these three pictures with measurements or no measurements if it's spiral. So I'm just trying to give you a quick little grade boost right at the end before the semester ends, before your finals. Something to just help your grade if you need it. If you don't do it, it's going to hurt your grade, but it's really simple. So go ahead and, find some pictures, measure it, get three ratios. So if you need help with this, like I said, we have class only on Thursday. Several of you may need to be here Thursday because you didn't turn in the test, so your grades drop below 70. But that's it, guys. This is our last lesson. If I don't see you again, because you'll be exempt, have a great summer. Hope to see you in the fall. But if going back to the school in the fall, man, do great. Do great. Remember our time here in Virtual and have fun this summer, guys. So that's all I got for you.